Hi all, welcome to the sixth lecture where we will be finishing the base decision criteria. So as we left in the last lecture, in this lecture particularly, we'll be picking it up from this place. We'll be expanding the base risk, and from there we would be trying to deduce a test statistic that would be showing us how to calculate the threshold when there are certain information that are given. So if the Neyman-Pearson criteria already gives us a particular threshold, why do we need another decision criteria? As I explained, this is simply because I have more information to incorporate to make a decision. When I have more information, I need a little sophisticated model to be able to include all the nuances of what is available to us. Okay. So anyway, let's dive into the mathematics. I have discussed about the goal, what we want to achieve in the last lecture. You can look into it if you wish to, if you have not watched it. So right now we'll be expanding this, which we already did in the last lecture. So EC would be equal to C00 P0 and Z0 PR given not R dr plus C01 P1 Z0 P R given H1 R dr plus C10 P0. I have described this in detail how this comes in the last lecture. R given H0 R dr plus C11 P1 integration of Z1 H1 R dr. Now if we want to find out a criteria, the best thing or the easiest thing that we can do is to club all of the expressions together, all of the integrals together. The best way to do this is obviously if we write all these integrals in just one region. Right now it is separated into two regions. Before going further, please note that the regions Z0 and Z1 or Z0 and Z1 are totally disjoint. Okay, that means they got no overlap. Because they have no overlap, we have one condition that comes out of it. What is that? That is, if there is a PDF and we divide that into two regions, the area under PDF, the area under a probability distribution function is always 1. So that will be equal to the area that is individually contributed by the region Z0 and the region Z1. So basically we can write Z1 in terms of 1 minus Z0. Okay. So we can write the area under Z1 to be 1 minus area under Z0. This is the freedom that we'll be going to exploit here. Or else you could have written Z0 equal to 1 minus Z1. It would not have made much difference. So what I wish to say is, let's keep any one of the expression. For example, let's keep the region Z0 here. Let's find out the integration for only the region Z0 for the entire term. So I'm changing this. So C00 P0, let the Z0 term stay as it is. Now as you see, I'm taking a high dimensional vector here in for the observation, because it is not necessary that it is always a one-dimensional observation. Anything a little complex, it can be well generalized with this expression. Anyway, C01 P1 Z0 PR given H1 R dr plus C10 P0. Now this Z1 I can write in the form of 1 minus Z0 PR given H0 R dr plus C11 P1 1 minus Z0 PR given H1 R dr. Okay. So you see what did I do? I converted all the expressions which were in the region Z1 into Z0 by exploiting this particular property, by exploiting the fact that Z0 and Z1 are both distinct regions in the space. Okay. All right. Now let's club all of the expressions together. This is very obvious, very trivial. So from here we will be getting C10 P0 plus C11 P1. We will be getting this as a different term. Okay, C10 P0 plus C11 P1. Now let's keep this expression as it is. Okay, apart from that expression, if we try to club the rest of the expressions together, it will somewhat become like this: C00 P0. Like if I try to club the R given H0 part, this is one R given H0, this is one R given H0. So this would be C00 P0 minus C10 P0, and this is P R given H0 and R dr. Okay, now what you can actually do is the P0 which is common in both the terms, you can just put it out, just for the sake of simplicity, because the priors and the cost are already given to you in the problem. Okay, and similarly you can also write Z0 here, or else you can do one thing. Instead of making it in a different integral, you can actually put all of it into one integral. Okay, so plus this is for P of R given H1, so this is C01 P1, and from here R given H1 you can find C11 P1. So C11, and let me keep P1 outside, and then you have P of R given H1 R. Now this entire expression, you have the integral. Okay, so please remember we have an expression here, and how is this expression? This expression is nothing but the entire integral. We actually have both the PDFs. We actually have both the PDFs included here, and it is integrated under the region Z0. Okay, all right. Now we shall be doing a little manipulation here. Please understand that there are costs associated. There are 4 kinds of costs associated, which I have discussed in the last lecture. You must understand that for a wrong observation, for an observation which is anomalous, the cost incurred by the system should be more. For the system to be more efficient, we need to throw in more cost when there are wrong outputs or wrong signals being sent. Okay, in that case the cost would be more. The cost of making right decisions, right observation will always be less. So in that regard, you can see that C00 must be less than C10, because C10 is the cost of making a wrong decision. So this entire term would be negative. Given the priors and the PDFs are always positive, this expression would come out to be negative. But here at the same time, C11 would be less than C01, so this expression would be positive. So in order to make both the expressions positive, why don't we just change the sign? We take the negative term here, and when we take negative out of here, C00 will be negative and C10 will be positive. This is what we'll be implementing in the next part. Okay, this is what we shall be implementing right now. So this expression E of C, this turns out to be C10 P0 plus C11 P1, and plus integration of Z0 C01 minus C11 P1 PR given H1 R dash minus C10 minus C00. This is what I have taken the minus common, and it's negative, so it's placed in the right hand side. PR given H0 R. Okay, and this entire thing is under integration. Now if our observation that we have, if our observation, let's say it belongs to the region Z0, our entire idea is to minimize this entire expression. Okay, now if we want to minimize this entire expression, please try to understand this, that we have the costs and the prior to be constant. So actually we don't need to bother with what the value of this is. Our main concern, or rather what we want to focus, is on the value of this integral, because this is what would decide the boundary, just as the NP criteria. Okay, so in a very similar way, if we have, let's say R, it belongs to Z0, the region Z0 in in the case we would be throwing it into the hypothesis H naught, then this entire expression, for it to be minimal, must be less than 0. This is what I mean. P1 P of R given H1 R minus C of 1 0 minus C 0 0 P0 P of R given H naught R, this must be less than 0. If this is negative, this entire term which is under the region Z naught would be minimum, or rather this is the boundary condition for it. Okay. If this is so, can I find the test statistic? So how do I find the test statistic? When it's an inequality, you take this into this side. So this will inevitably become, this negative sign would become less than this. Okay. Why did I do it like this? So that both the terms come out to be positive. This is a positive term, this is a positive term. So there is no issue. Now what I would do is, I would take this distribution and I would take this distribution and divide it. So I am having P of R given H1 R divided by P of R given H naught R is less than P naught C 1 0 minus C 0 0 divided by P1 C01 minus C11. See, when this is less than this particular expression, this region is actually in Z naught. In that case, it would fall under hypothesis H naught. Okay, the null hypothesis. This is how we have designed the LRT or the test statistic. So in this case, the test statistic or the sufficient statistic, there are two terms to represent this. Either this is test statistic or sufficient statistic. Okay. Now any term you can use, or LRT. The likelihood ratio test is once again the ratio of both the probability distributions. And very interestingly, the threshold here, this particular expression is the threshold. We can decide the threshold very easily. Like in Neyman-Pearson criteria, we had to have the false alarm, the probability of false alarm to find the threshold. Here in this case, if you are given the prior and the cost for each of the cases, then we can easily find out the threshold. And if this is greater than the threshold, then of course we have the alternate hypothesis to be true. Okay. So this is how the LRT can be set up in a very usual way. So if I try to make the idea of test statistic a little bit mathematical, I mean, if I want to summarize this expression, let me summarize this expression. So this becomes our test statistic. This is P of R given H1 R divided by under hypothesis H naught R. Now this should be greater than the threshold. The value of the threshold I already told what it is. So once again, if you want to revise, this is the value of threshold. So if you're given all this information, then you can just find out the threshold just like that. Is it not interesting? This is so straightforward. If you're given the prior and cost, it becomes so easier. Okay. So if we talk about the region Z naught, what will it be? These are the observations where this LRT is less than the threshold. And if I talk about the region Z1, what would it be? The region where the observations, the LRT is greater than the threshold. As simple as that. This is the Bayes decision criteria. Remember, the threshold, the idea of threshold remains the same, because we are trying to find out a decision criteria, but the expression for threshold comes out to be this under the given circumstance. Okay. Now let's quickly solve a problem. Solving problems are very similar in nature. So here, what do we have? We have a n-dimensional vector as a signal. So here we have the signal or observation. So there are observations under two hypotheses. And remember, this is an n-dimensional observation. So the first one is under hypothesis H0 and the second one is under hypothesis H1. So the first one, this is an expression plus n. N is Gaussian white noise. What is Gaussian white noise? Gaussian white noise means all the noise are uncorrelated with each other, because R1 has a noise, R2 has a noise, Rn has a noise. All of these are non-correlated. These are not correlated with each other. Okay, that's called as white noise. That's uncorrelated noise. Okay, all right. So now it is also given that M1 is greater than M0. So M1 you can take it to be any constant value, a constant value. For example, we took DC amplitude, for example. So this is a constant value and it's just given that M1 is greater than M0. So one of the fundamental assumptions to solve all this kind of problems, you might have seen that all the noise what we have, first of all, these are Gaussian white noise. So just about the noise, if I talk about, the distribution of that noise would be 0, and it's of standard deviation sigma. But all of these are IIDs. Okay, these are independently distributed and identical. This is very important. These expressions, as I'm telling again and again, these are very important to solve the problem. Had it not been there, it would have made the problem much more complex. Okay, so what does it actually mean? This means that what does, for example, this expression mean? This means that R1 R of k given H1. So this is, for example, R1 given H1 will be equal to M1 plus N1. R2 given H1 will be M1 plus N2. R3 given H1 equal to M1 plus N3. So the amplitude of all the signals are the same and the added noise would be different. Okay, so this is all what it means. All right. Now, as I said, because there are no specificity on the noises, so we'll be assuming all of them with a standard deviation of sigma. Okay, until and unless stated. If it is stated that all the noise would be having different standard deviation, it would make the problem different once again. Okay, now because each one of these observations that we have under a particular hypothesis, each one of those observations which form a vector of observations, we can form an expression for this. So let's set up the LRT. This would be P of R given H1 by P of R given H0, the observation. Okay, now because these are identically independent and identically distributed IID, we can actually give the multiplication of all of the observations. Okay, P of RK given H1 RK divided by K is equals to 1 to N P of RK given H0 and RK. Okay, now what we are left to do is just expanding this. Now this is the LRT. If this is greater than the threshold, we have the hypothesis H1. If it is less than the threshold, we have the hypothesis H0. Okay, so let's solve it. So we are not left with much. So if we try to have a multiplication of all of those expressions, so we will be having the Gaussian, that is 2 pi sigma square, and exponential. As I said, all the all the signals under hypothesis H1 are being shifted by M1. So we'll be having RK minus M1 whole square divided by 2 sigma square, and all the hypotheses under H0 are being shifted by M0. So this is what we shall be giving in the denominator. As I said, the standard deviation remains the same. These are independent, identically distributed. RK minus M0 whole square by 2 sigma square. Now this is greater than or less than, let's keep the threshold for later. Let's just solve it. Okay, so this gets cancelled out. As you know, this is an exponent, so all these terms will get summed up, all these terms. So basically the product will be a sum in the exponent. So we'll be having exponent sum of k is equals to 1 to n minus rk minus m1 whole square by 2 sigma square divided by exponent of summation of k is equals to 1 to n minus of rk minus m0 whole square by 2 sigma square. Okay. Now once again two exponents are divided, we can subtract them. So we get exponent of minus summation of rk minus m1 whole square by 2 sigma square minus summation of rk minus m0 whole square by 2 sigma square. So what did we actually do? We took out the negative term and we just kept it as it is. Okay. Now this is greater than or less than some eta. This is the threshold. Okay. Now we'll be acting on threshold to find the test statistic to see on what the test statistic would actually depend upon. Okay. So let's reduce this expression. Let us take logarithm in both sides. Okay. All right. So if you take logarithm in both sides, you will be having summation of rk minus m1 whole square plus summation of rk minus m0 whole square. It will be greater than or less than 2 sigma square ln eta. Okay. All right. 2 sigma square which was divided, we took it into the right hand side. So now let's expand the summation. This is a very trivial job. This is rk whole square plus m0 square minus 2 m0 rk minus rk square plus 2 m1 rk minus m1 square, that is greater than or less than 2 sigma square ln eta. Okay. Now let's just cancel out the terms. Rk and rk gets cancelled out here and we'll be left with 2 times here m1 minus m0. Now because m1 and m0 are constant, this will be summation of k is equal to 1 to n rk. All right. And from this expression, see m0 square and m1 square would be constant and it would be summed up n times. So we would be having n times m0 square minus m1 square. This would be either greater than or less than 2 sigma square ln eta. Okay. Now let us try to reduce it down further. So what we'll be doing is we'll be dividing the entire expression by n first, and then we shall be throwing up this expression to this side. This is a constant expression. So just by rearranging, we would be having 1 by n summation of k is equal to 1 to n rk, that will be greater than or less than sigma square ln eta by n m1 minus m0 plus m1 plus m0 by 2. Okay, this is a very interesting observation, by the way. So you can easily see this, right? We divided the entire expression by 2 times m1 minus m0, and whatever we were left with, this entire expression, a square minus b square is a plus b into a minus b, so this gets cancelled out and we are left with this expression. Now if we take this in the context of communication, but this is the entire result. This is the test statistic that we have. Now the test statistic is the average of all the observations. See this 1 by n term. This is important. This is what I brought out intentionally here. Okay. So the test statistic I have is the average of all the observations, as simple as that. When we are given the case of independently distributed noise, Gaussian white noise with mean being shifted, and even if there are vectors, we have the LRT or we have the test statistic to be the average of all the observations. Now this is ideally. If we try to look at it from a communications standpoint, you know that this eta is actually P0 by P1, C10 minus C00 by C01 minus C11. Okay. Now, for example, we take out the situation where the priors P0 and P1 are both equal. Let us assume this, okay? This is not always the case. I'm taking a special case just to show something. So the priors P1 and P0 are equal. For example, equally likely cases of the two observations or of the two possibilities. So this gets cancelled out, and this entire expression C10 minus C00, C01 minus C11. Ideally, we are taking C10 to be 1, C01 to be 1, and C00 to be 0, C11 to be 0. The cost of wrong decision is maximum, that is 1, and the cost of the right observations, the right ones, are 0. This is the ideal scenario. Okay, so eta turns out to be 1 in this case. This is under a very specific scenario. Now if eta is 1, this entire term gets cancelled out. Remember, this is a very specific case I am discussing in the context of communication. Then, very interestingly, we would be having the threshold, or the threshold can be decided just with this expression, just with the average of the mean value, the mean DC value of the signal under both hypotheses. Just this. If you just have the average of them, you will be getting a threshold. Is it not interesting? Is it not very interesting? This is one observation that I wanted you to note. Now, once again, this is very problem specific. That's why I'm telling. There are not many problems that can be formed on this, but at the same time, significantly, you can enhance your concept with this kind of problems, which give you a glimpse as to how a test statistic can be formed and how those are related. How test statistic can sit on mean, sit on variance, depending on various problems. It just depends on problems. Okay. So with this, we have actually finished the base decision criteria today. So in the next lecture, we'll be taking our last decision criteria, that is the mean max decision criteria. Okay. So just as I said, that it depends on what is given to us. When almost nothing was given, we just had the conditional PDF. We took out the NP criteria. A little more information, we have base criteria, and it is not necessary that always we have all the information at hand, right? So in some cases priors might be associated, in some cases priors might not be associated. It totally depends on the problem. We will see a new class of problems in the next lecture, that will be a mean max criteria for detection. Okay, so we will be covering the basics of the detection criteria when we have only two decisions to make, when we have only two hypotheses, when we are obligated under the case of binary hypothesis. Okay, so I hope you found this lecture fruitful. If you have any kind of comment, if you have any doubt, please feel free to comment and I would try to respond. Okay, this is not easy. You might need to view the lectures multiple times to understand it. In the next lecture, or might be in the upcoming lectures, I'll be telling you the textbook which you can follow. But at the same time, all the information in the textbook might not be relevant and it might become overwhelming at times. So this lecture series can actually suffice if you try to understand all the points very subtly and in the requisite depth as it is needed. Okay, a very thorough concept of probability and statistics is needed, or a very fundamental grasp of that is needed, as I told you. So let's keep the lecture up to this today. Let's meet next week for completing the min-max criteria. Thank you very much.